Welcome back. Today, we're tackling something absolutely massive. We're diving into Module 10 of this explainer, focusing on FPSO fire protection. You know, a floating production, storage, and offloading vessel isn't just a ship. It is literally a giant industrial refinery floating right on top of millions of barrels of highly flammable crude oil. Oh, and it's doing all of this out in the middle of the ocean. The safety engineering required to stop these things from turning into absolute disasters is just phenomenal. We're going to break down the detection systems, the structural barriers, and those heavy-duty suppression tactics that make offshore survival even possible. Let's get right into it. To really get why this matters, we have to look at how completely different an offshore fire is compared to one on land. I mean, think about it. If an office building or a land-based refinery catches fire, the drill is pretty simple, right? You evacuate to a safe distance, you dial emergency services, and you wait for the professional fire brigade to show up. But on an FPSO, you are entirely surrounded by sea. There's nowhere to run, and calling 911 just isn't an option. You are the fire brigade. The whole facility has to be this completely self-contained, self-reliant defense fortress. Okay, let's dive into this. Here is the mental map we'll use to look at our concentric layers of defense. We'll start with the offshore fire challenge, move into passive fire protection, then active fire suppression systems, machinery space suppression, and finally, the human element. Section 1. The Offshore Fire Challenge. Let's look at the baseline philosophy here. Before we get into the actual hardware, we've got to understand the core philosophy that dictates everything from the keel up. As this quote spells out, the brutal reality offshore is that your fire protection systems aren't just there to save property. Their main job is survival. Since you can't just walk away, the engineering has to automatically suppress and ideally completely extinguish the threat. If it can't put the fire out, it absolutely must contain that extreme heat and those flames long enough to buy the crew precious minutes to abandon ship. It is, literally, a race against time. Moving on to Section 2, passive fire protection. This is our outermost layer of defense. So this is your first line of defense, and honestly, what's so fascinating about it is that it requires exactly zero human intervention. No power, no automated triggers, nothing. Passive fire protection, or PFP, is a permanent automatic shield built right into the steel of the vessel itself. You really have to think of an FSPO not as one giant open ship, but as a honeycomb of tightly sealed, fire-resistant zones. By dividing the vessel up with structural and thermal boundaries, PFP makes sure that if a fire starts in one specific module, it's physically walled off from the rest of the ship. It keeps the beast trapped right where it was born. Now, what's really interesting about this slide is the escalating scale of engineering needed to deal with different kinds of fires. Because, let's face it, not all fires burn the same. At the baseline, you've got your A-class divisions, like an A60 bulkhead, which handles standard cellulosic fires for up to 60 minutes. But we're on an FPSO, dealing with pressurized crude and gas. So you need H-class boundaries for hydrocarbon fires, which burn way hotter and much faster, and those are rated for up to 120 minutes. And at the absolute extreme, we have the J-class for jet fires. Imagine a directed, high-velocity flame from a high-pressure gas release acting literally like a blue torch. It'll rapidly erode normal steel and fireproofing. That's why J-class protection is absolutely mandatory around your highest pressure equipment like gas compressors. And this brilliantly illustrates just how thorough these boundaries have to be. Look at this A60 bulkhead. It's designed to limit the temperature rise on the safe, unexposed side of the wall to an average of just 140 degrees Celsius for a solid hour, even while a literal inferno is raging on the other side. But, a thick steel wall is completely useless if fire can just sneak through a tiny gap. Notice how every single pipe and electrical cable passing through has to be meticulously packed, sealed, and certified to match that exact same A60 rating. The integrity of the whole zone completely relies on these tiny, crucial details. All right, Section 3, active fire suppression systems, the dynamic weapons on board. So, the crucial point is redundancy. If passive protection is the stationary armor of the FSPO, the active systems are the offensive weapons meant to actually fight the fire. And on an FSPO Firewater ring main, 100% redundancy is completely non-negotiable. Since there's no city fire hydrant to hook up to, the vessel must have at least 2 independent fire pump trains. And get this, each one of those single trains has to be fully capable of supplying the entire design flow demand all by itself. That's vastly more stringent than land-based setups. If one pump gets taken out by an explosion or is down for maintenance, the vessel still has its full firefighting capability ready to go. And it isn't just about having extra pumps, it's about how you power them. When there's a major gas leak or a fire, the FPSO initiates an emergency shutdown, or ESD. This often intentionally trips the main generators just to kill any ignition sources. Because of that, these massive fire pumps must be completely independent from the main power grid. They usually run on their own dedicated, heavy-duty diesel engines, or they run off a totally separate emergency power supply. They have to flawlessly push water even when the rest of the ship goes completely dark. Let's move to and see how this builds with the primary delivery mechanism for all that massive water supply, the fixed water deluge system. Now, don't confuse this with the sprinklers in a regular office building that pop one at a time right where the heat is. A fixed water deluge system on an FPSO process deck uses open spray nozzles. The second the fire and gas detection loop triggers, a deluge valve opens, and every single nozzle in that zone activates simultaneously. It instantly blankets the whole module in this massive, dense wall of water. The sheer volume of water moving here is just staggering. The design application rate for an FSPO process area is a minimum of 12.2 liters per minute per square meter. That's not just some random statistic. That specific volume is the absolute physical threshold needed to absorb the extreme heat of a hydrocarbon fire and stop the heavy structural steel from rapidly losing its strength and collapsing. The goal isn't necessarily to put the pressurized fire out, which can actually be super dangerous if gas is still leaking, but to keep the equipment cool while the emergency shutdown system depressurizes the plant. Section 4, Machinery Space Suppression. Now we're heading deep into the core of the vessel. As we step off the open process decks and head down into the enclosed engine rooms and turbine halls, we're looking at entirely different hazards. You can't exactly dump thousands of gallons of raw seawater onto highly sensitive, multi-million-dollar electrical generators. So, enclosed spaces use two primary methods. First up is water mist. This uses incredible pressure to create microscopic water droplets that flash into steam, absorbing massive amounts of heat. The second method is CO2 total flooding. This is a gas-based system, and instead of cooling the fire, it violently displaces the oxygen in the room down to a level where combustion is physically impossible. A heavy-duty CO2 fixed firefighting package like this is unbelievably effective at smothering a fire that's hiding deep inside complex machinery where water just couldn't reach. Since it's a gas, it penetrates every single corner of the compartment, choking the flames out incredibly fast. But using this ultimate suppression system brings up a really dark and critical caveat. To successfully put out a hydrocarbon fire, CO2 requires a concentration of around 34% or higher. Well, at that concentration, it is completely lethal to human beings. If a CO2 total flooding system activated in an occupied engine room, it would literally be a death sentence for anyone trapped inside. Because of this grim reality, the system requires strict automated pre-discharge alarms. You have to have a complete and verified evacuation of the space before the gas is released. It really highlights how offshore engineering is this constant tightrope walk between fighting the hazard and protecting the crew. Section 5, the human element, our final safety net. We've talked a lot about steel barriers, automated deluge valves, and lethal gas systems. But if all those automated systems fail, the innermost layer of defense is the brave men and women living on board. Turning a normal maritime crew into an elite fire brigade requires highly regulated gear. They don't just grab a hose and run in. The crew uses remote stops from safe muster stations to shut off ventilation fans and fuel lines. They deploy offshore certified portable extinguishers for immediate response. And the dedicated fire team, they suit up in heavy, heat-resistant firemen's outfits, complete with self-contained breathing apparatus, or SCBA. That gives them 30 to 45 minutes of independent, clean air to fight fires inside a highly toxic, smoke-filled environment. But listen, all of this multi-million-dollar engineering and specialized gear is completely useless without rigorous practice. SOLAS regulations mandate monthly fire drills that require a full muster of all personnel on board. And these aren't just simple roll calls. They constantly vary the scenarios to exercise every single emergency response capability, everything from an engine room fire to a massive hydrocarbon leak on the process deck. Operational readiness comes down to muscle memory. Every single person has to know exactly what to do the second those alarms sound. So, even with A60 bulkheads, 100% redundant fire pumps, massive water curtains, and a highly trained crew, what happens if the fire is just too big? What happens when containment fails? The heat gets absolutely unbearable, and they actually have to give the order to abandon ship. That is the ultimate nightmare scenario, and dealing with it requires a totally different set of life-saving appliances. In Module 11, we're going to explore exactly how the crew escapes a distressed FPSO using lifeboats, life rafts, and immersion suits. Thanks for tuning into this explainer, and I'll catch you in the next module.